Hello, everyone, and welcome to our next lecture in pre-calculus algebra. I think this is lecture 10, and this lecture has to do with functions. That's funny, that doesn't look like functions. Well, I guess before we talk about functions, we're going to have to talk about relations. A relation from a set x to a set y is a rule that assigns to each element in set x one or more elements in set y. And instead of saying one or more elements in set x, one or more elements in set y, I guess we could say at least one element in set y. So a relation from a set x to a set y is a rule that assigns to each element in set x at least one element in set y, one or more elements in set y. Here's an example, and we have a rule going from set x to set y. Is this rule a relation? Let's check it out. Does it assign to each element in the set x at least one element in the set y, one or more elements in the set y? To the element to the element 1 in set x, the rule assigns the element a in set y. To the element 2 in set x, our rule assigns the element b from set y. To the element 3 in set x, our rule assigns the element c in set y. And to the element 4 in set x, our rule assigns the element d in set y. So we can say that this diagram depicts a relation from set x to set y because this diagram assigns to each element of set x at least one element from the set y. So this diagram depicts a relation from set x to set y. Let's look at more examples. We are back, and we have an oh, by the way moment. Oh, by the way, the set x of a relation is called the domain of the relation, and the set y is called the range of the relation. So a relation assigns to every element in the domain at least one element from the range. Let's see if that happens here. Here's an element in the domain x. Does our rule assign to the element 1 at least one element from y, the range? Yeah. It assigns the element a in our range to the element 1 in the domain. What about the element 2 in the domain x? Does our rule assign to the element 2 at least one element from the set y, the range? Yeah, it does. Our rule assigns the element a to the element 2. Now, does it matter that the element a is assigned to both elements 1 and 2? Nope, not a problem, not a problem. To the element 3 of the domain, our rule assigns the element b from the range. To the element 4 in the domain, our rule assigns the element C from the range. And to the element 5 in the range, our rule assigns the element C in the range. And it doesn't matter that both elements 4 and 5 in the domain are assigned the same element C in the range. So it is a fact that this rule assigns to every element in the domain at least one element from the range. So this is a relation. More examples. Here's something a little bit different. Some elements in our domain are assigned more than one element in the range. Is that a problem? You know, it isn't. Our definition of range says that every element, our definition of relation says that every element in the domain is assigned at least one element from the range. Our alternate definition says every element in the domain is assigned one or more elements from the range. So here, the element x in the domain is assigned two elements, A and B, from the range. For a relation, that's not a problem. The element 2 in the domain is assigned the element C in the range, at least one element in the range. No problem here. The element 3 in the domain is assigned two elements. The element 3 in the domain is assigned two elements in the range. One or more elements in the range. Not a problem. So based on what we just established, this diagram does define a relation from the set X to the set Y. Let's look at one more example, but before we expand our discussion to include a special kind of relation, which is called a function. So let's look at one more example. Okay, this is our final example when we're talking about relations in general. And this diagram depicts a candidate for being a relation. Let's see if this actually is a relation. Our definition says that a relation is a rule that assigns to each element in the set X, the domain, at least one element from the set Y, the range. Or it assigns to each element in the set X one or more elements from the set Y. This element in the domain looks rather suspect, doesn't it? Does our rule, as depicted by this diagram, assign the element 4 at least one element from the set Y? It doesn't, does it? So this diagram does not define a relation. This diagram fails the relation test. The reason is this element 4 of set X is not assigned at least one element from set Y. So this is not a relation from set X to set Y. Next, we're going to talk about a special kind of relation. And this kind of relation is called a function. Okay, new stuff. A function from a set X to a set Y is a rule that assigns to each element of set X exactly one element from set Y. So a function is a rule. You know what? I can do a little bit better than that. A function, it is a rule, but I can say it's a relation A function is a relation that assigns to each element of set X exactly one element from set Y. If you can't see this word, it's relation. A function from a set X to a set Y is a relation that assigns to each element of set X exactly one element from set Y. So a function is a special kind of relation. A relation from a set X to a set Y is a rule that assigns to each element of set X at least one element from the set Y. A relation can assign to an element from set X more than one element in set Y. A function can't do that. A function from a set X to a set Y assigns to each element of set X exactly one element from set Y. One element from set Y, no more, no less. So let's look at some examples. And when I work with functions, I like to give them names, and oftentimes we give our function the name f. Some very smart person centuries ago thought of this and said, hey, how about f for function? And it stuck. So we'll call this function f, and we'll actually denote that it's a function by putting its name right up here. Now, is this really a function? I claim it's a function. If it is a function, then it will assign to each element of set X exactly one element from set Y. Does that happen? This element 1 in set X is assigned the element A from set Y, exactly one element from set Y. This element 2 in set X is assigned the element B from set Y, exactly one element from set Y. This element 3 from set X is assigned the element C from set Y, exactly one element from set Y. And this element 4 from set X is assigned the element D from set Y, exactly one element from set Y. So yes, this is a function. Every element in set X is assigned exactly one element, exactly one. No more than one, no less than one element from Y. So that is a function. Let's look at some more examples. New example. This one has a slightly different appearance than the one that we looked at before. Let's give it our careful consideration. The element 1 in set X, the domain, is assigned the element A from set Y, the range. So, element 1 is assigned exactly one element. Element 1 in set X is assigned exactly one element in set Y. Now let's look at this one. Element 2 is assigned what element in set Y? Element 2 in set X is assigned the element B in set Y, right? So element 2 in set X is assigned exactly one element, B, in set X. No problem. Element 3 in set X is assigned exactly one element, set Y, element B. Does the fact that elements 2 and 3 in set X are assigned the same element in set Y cause a problem here? Nope. The fact that 2 and 3 in set X are assigned the same element in Y, the range, in no way disqualifies this from being a function. Each element, 2 and 3, are assigned exactly one element from set Y. It just so happens that 2 and 3 are assigned the same element from set Y. But nevertheless, 2 is assigned exactly one element from set Y, B. 3 is assigned exactly one element from set Y, B again. That's all that matters. And element 4 in set X, the domain, is assigned exactly one element, C, in set Y, the range. So we can say, quite honestly and accurately, that every element in set X, the domain, is assigned exactly one element in set Y, the range. So this is a function. More examples. This diagram gives us our next candidate for function. And we'll see if this diagram, as it defines a relation here, also defines a function from set X to set Y. And let's see. We have the element X, we have the element 1 in set X. And this element 1 is assigned two elements from set Y. Element 1 in set X is assigned both element A and element B in set Y. So can we truthfully say that the element 1 in set X is assigned exactly one element from set Y? No. Element 1 is assigned more than one element from set y. And you know what? This sort of thing happens again. Look at the element 3 in set x. Can it be said that the element 3 in set x is assigned exactly one element from set y? No. Element 3 in set x is assigned both d and e. Element 3 in set x is assigned more than one element from set x. That's fine for a relation, but with a function, we stipulate that every element in the domain, set x, has to be assigned exactly one element from the range, set y, and that doesn't happen. Okay. Now let's print the bad news. And we'll give our reason here. Element 1 in x is assigned more than one element from set y. If we have a function, every element in set x has to be assigned exactly one element in set x. That doesn't happen here. It doesn't happen here. There used to be an E at the end of the word one. I don't know what happened to it. So this fails to be a function. Let's continue with one more example before we move to a different way of denoting functions. Again, we have a diagram that depicts a candidate for functionhood. We want to know if this diagram, as it's drawn, represents x as a function. If it does, if f is a function, then every element in set x is assigned exactly one element in set y. The element 1 in set x is assigned exactly one element in set y. The element 2 in set x is assigned exactly one element in set y. The element 3 in set x is assigned exactly one element in set y. The element 4 in x is, the element 4 in x is not assigned any element in set y. This diagram does not represent a function from set x to set y, because this element in set x, the domain, is not assigned exactly one element in set y. As a matter of fact, it's not assigned any element in set y. and set y. And here's our reason. Element 4 in set X does not assign exactly one element from set Y. In fact, 4 does not assign any element from set Y. So this pretty much covers our pictorial explanation of relations and functions. We're going to look at different ways to define relations and functions now. Alternative representations of functions and relations. The first alternative way of representing functions and relations is by sets of ordered pairs. And remember from the graphing that we did about a week ago, given an ordered pair of real numbers, AB, the first coordinate is the x coordinate, and the second coordinate is the y coordinate. So this is the x coordinate, A, and B is the y coordinate. And if we were graphing this, A would be a point on the x-axis, and B would be a point on the y-axis. So we associate the ordered pair AB with sets x and y. This is our x coordinate. This is our y coordinate. Now let's see how we can take a set of these ordered pairs and somehow turn that into a relation or a function. Here's our first alternative to defining a function or a relation. A set of ordered pairs can be used to define a relation or a function from a set x to a set y as follows. Every first coordinate or every x coordinate of an ordered pair represents an element of the domain x. So the first coordinates or the x coordinates of the ordered pairs represent elements of the domain x. Every second coordinate or y coordinate of an ordered pair represents an element of the range y. So all of the second coordinates or y coordinates represent elements of the range. And let's look at just one example. This is the first element or x coordinate. So this 1 is an element of the domain x. And what about this second coordinate, this y coordinate? This second coordinate or y coordinate indicates that 2, boy, that's a horrible 2, is an element of the range y. So representing a function in this way, we'd look at the 1 and say, aha, this is the first coordinate, the x coordinate, so 1 is an element of the domain x. Oh, and here, this 2, this indicates that the element 2 is an element of the range y. And it actually indicates something a little bit more than that. Okay, I think this completes the thought very nicely. We're using this ordered pair to help represent the function. And the first coordinate, or x coordinate being 1, tells us that 1 is an element of the domain x. This second coordinate, or y coordinate, 2, tells us that 2 is an element of the range y. And it tells us a little bit more. It tells us that the element 2 of the range is assigned to the element 1 of the domain x by the function or the relation, whatever it is we're working with. So let's look at sets of ordered pairs as they define a relation or a function. Here's a nice little exercise. Determine whether the set of ordered pairs -1, 2, 0, 1, 1, 2, 2, 5 represents a function and or a relation. So let's investigate that. And let's also tie this back to the way that we were representing functions and relations previously. We had set x, and we had set y. And remember, the first coordinates are from the domain x. So the domain has elements 1, 0, I'm sorry. The domain has elements -1, 0, 1, and 2. There's our domain. The range has elements 2, and the range is the y coordinates, right? So the range has elements 2, 1, 2, 5. 2, 1, and we already did 2 and 5. This is our range. But the ordered pairs tell us a little bit more. The ordered pairs tell us how the function or the relation assigns to each element of the set X at least or exactly one element from the set Y. This tells us that -1 of the domain is assigned to the element 2 from the range. Okay, -1 is assigned the element 2. This tells us that the element 0 in the domain is assigned the element 1 in the range. Okay, 0 in the domain is assigned the element 1 in the range. And this tells us that the element 1 in the domain is assigned the element 2 in the range. So here the element 1 in the domain is assigned the element 2 in the range. No problems here. And the element 2 in the domain is assigned the element 5 in the range. Now let's see. Every function is a relation. Every function is a special kind of a relation in which every element in the domain is assigned exactly one element in the range. So let's test this to see if it's a function first. If it is a function, we'll know that it's automatically a relation also. Let's look at this guy in the domain, -1. It's assigned the element 2 in the range. So -1 is assigned exactly one element, 2 in the range. 0 in the domain is assigned exactly one element, 1 in the range. Looks good. 1 in the domain is assigned exactly one element, 2 in the range. Now, -1 and +1 are both assigned to the element 2 in the range, but that's okay. This element, -1, is assigned exactly one element from Y, the element 2, and this element in the domain, X, is assigned exactly one element in the range, 2. No problem. It's okay if these two guys get assigned to the same element. The element 2 in the domain is assigned to the element 5 in the range, exactly one element in the set Y, is assigned to the element 2. So this is a function. Every element from X is assigned exactly one element from the set Y. So this is a function. And since every function is a relation, this is also a relation. Now let's focus on this example a little bit more, but instead of looking at this diagram, we'll look at the ordered pairs. What was it that would have disqualified this as being a function? What would have disqualified this as being a function would have been if we had one element in set X being paired with at least two elements of set Y. Remember, a function takes an element in set X and it assigns it exactly one element in set Y. So in order for this not to be a function, we'd have to have some element in set X assigned to not exactly one element in set Y, but more than one element in set Y. Ooh, that would be a problem. Now, what would that look like if we're looking at ordered pairs? Let's say, for example, that this failed to be a function because in addition to -1 being paired with the element 2 in set Y, -1 was also paired with this element in set Y. If we had -1 paired with these two elements from set Y, how would that change what we have up here? Let's see, wouldn't we have -1 for X and +1 for Y? We'd have another ordered pair here, -1, 1. And how would that tell us that, this is not a function? What would it be about these 5 ordered pairs that would tell us that these ordered pairs don't represent a function? It would be the fact that this X coordinate appears twice. And that would indicate that some element of the set X has assigned to it two different Y values. Not exactly one Y value like a function should have, but two different Y values, 1 and 2. So that would be the telltale sign for a set of ordered pairs representing a relation not to be a function. no, let's see, 2. If something like this happens, where we have a set of ordered pairs, and 2 of these ordered pairs have the same x value, this means that the same x coordinate would be assigned to 2 different y coordinates, or that 2 y values are assigned to the same x value. See that? We have 2 different y values, 1 and 2, assigned to the same x value. So we can't say that every x value has exactly 1 y value assigned to it. So if this sort of thing happens, same x value, different y values, not a function. Still a relation, but not a function. The set of ordered pairs, -2, -7, -1, 0, 0, 1, 1, 2, 2, 9, represents a function. No, whoa, 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 whoa. Let's put on the brakes here. Represents a relation from set x to set y. The first thing we do is give the domain and range of the relation. So the domain, that's the set of all x values. -2, -1, 0, 1, and 2. Those are the first coordinates or x values. And here's the range. The range is the set of all y values of the relation. So we have -7 and 0. Then we have 1 and 2. And we have 9. So this is the set of our y values, the range. And does this relation define a function from set x to set y? If so, every x value is assigned exactly 1 y value. That's the definition. Now, if an x value is assigned more than 1 y value, we're going to have 2 ordered pairs here that have the same x value, but a different y value. So if we have a relation that defines a function then every x value is assigned exactly one y value. In other words, no x value appears more than once. As an x value. So let's check this out. Let's just start at the first ordered pair, -2. Does -2 appear as the x value in any other ordered pair? Nope, 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 nope. Okay. What about -1? Does this appear as the x value in any other ordered pair? Nope, 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 nope. What about 0? Does 0 appear more than once as the x value? No, 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 no. 1, does that appear more than once as an x value? No, 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 no. 2, does that appear more than once as an x value? Nope, 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 and nope. No x value I wonder what these ordered pairs would look like in the xy plane. Okay, let's graph this son of a gun. Graph the function represented by these ordered pairs. X equal -2 and y equal -7, so that's down here. X equal -1, y equals 0. That's right here. X equals 0, y equals 1. That's y equal 1 is right here, and here's x equals 0. X equal 1, y equal 2. Here's x equal 1 and y equal 2. And then finally x equal 2, y equal 9. Here's y equal 9. X equal 2. Okay. Okay, so those are the points in the xy plane that give us the graph of our function. We have a set of ordered pairs here, and the question is, determine whether the relation given by the set of ordered pairs -1, 0, 0, -2, 0, +2, 1, 0 defines a function. And let's see, what if we have a relation already, what is it that disqualifies a relation from being a function? if a single x value is assigned more than one y value, as long as every x value is assigned exactly one y value, we got ourselves a function. But the minute that we have an x value being assigned more than one y value, it's not a function. And how would that show up here in our set of ordered pairs? See, wouldn't that show up when we observe that we have two different ordered pairs that have the same x coordinate? Ooh. Okay, two different ordered pairs with the same x coordinate, not a function. X equals 0 is assigned more than one y value. It's assigned -2 and +2. In order for this to be a function, every x coordinate has to be assigned exactly one y value. So this is not a function. And for future reference, let's see how this kind of plays out when we graph it. Let's graph this and see if we notice something that we can use in the future to determine whether the graph of something represents a function or not. This is the same example. We're just going to graph the points given by our relation and see if we can get something out of this that we can apply in future situations. X equals -1, y equals 0. That's right. Yeah. X equals 0, y equals 2. No. X equals 0, y equals -2. So that's right here. X equals 0, y equals +2. That's right here. And x equals 1, y equals 0. 1, 0. Now, what is this picture trying to tell us? Well, let's go back about 2 minutes and remind ourselves of why this relation does not define a function. Remember, we had 2 points in the relation, 2 ordered pairs in the relation with the same x coordinate. And that meant that we had 2 different y coordinates being mapped to the same x coordinate. So these 2 points are the problem. These 2 ordered pairs are the problem. They have the same x coordinate, 0. And in the xy plane, where are all the points that have an x coordinate of 0? In the xy plane, don't all the points with an x coordinate of 0 lie on the y-axis. And sure enough, this point and this point, both of which have an x-coordinate of 0, are on the y-axis. Now, the big thing about this is that these 2 points lie on the same vertical line. That vertical line happens to be the y-axis in this case. But any time that we have the graph of a relation and we have 2 points on that relation that lie on the same vertical line, then we ain't got a function. We ain't got none. Whoops. Here's the key observation. Here are the 2 troublemakers, the 2 troublesome ordered pairs, or the 2 troublesome points, 0 and -2 and 0 and +2. These 2 troublemakers both lie on the same vertical line. In this case, that vertical line is the y-axis. But the important observation is that these 2 troublemakers both lie on the same vertical line. The graph of this relation intersects a vertical line at 2 different points. Whenever this happens, the relation fails to be a function. Whenever the graph of a relation intersects a vertical line at 2 different points, the relation fails to be a function. I'm going to give this thing a name. It's so profound. Yep, we like this so much we actually give it a name. We call it the vertical line test. A relation defines a function exactly when the graph of the relation does not intersect any vertical line at more than 1 point. So if the graph of a relation doesn't intersect a vertical line, any vertical line at more than 1 point, it's a function. The relation fails to be a function exactly when its graph intersects some vertical line at more than 1 point. If there's a vertical line at which the relation or the graph of the relation intersects that vertical line at more than 1 point, it's not a function. If no such vertical line exists, in other words, if there isn't a vertical line where the graph of the relation intersects at more than 1 point, we got ourselves a function. And we will continue this lecture at another time.